Hello, in this video I'll explain the chain rule. So this is the chain rule right before you. So let me actually explain what this is saying. So the derivative of y with respect to x is equal to the derivative of y with respect to another variable, let's say u, times the derivative of u with respect to x. Now this is actually a very useful notation because we can actually see, if we look at this as literal multiplication, that the du's cancel out. And now we have left dy dx. So that should seem a bit strange to you because, this isn't literal multiplication. Derivatives are essentially limit evaluations. So this is actually true via a limit proof. However, I won't show you that. What I will show you is why this is useful and what this is used for. So this is actually used for function composition. So if we want to find the derivative of a composite function, we can actually use the chain rule to help us out a lot. So this is what function composition is if you happen to have forgotten. So first I'll let y equal f of g of x. So that's the notation of function composition. So that means g of x is stuffed inside of f of x. So let me actually take the derivative of this. So in the end, we want to take the derivative of y. We want dy dx is equal to f of g. Taking the derivative of y in this case will give us the derivative of f of g of x, which is ultimately what we want. So let's just put that aside. And let me actually undo this. And let me focus on this notation rather. So I'll say y is equal to f of g of x. Now first, what I want to do is make a substitution. I'll let u equal g of x. So we can actually rewrite this as y is equal to f of u. So what I'm going to do now is just to take the derivative with respect to u. And the reason being is because our function is in terms of u. So dy du is equal to f prime of u. So we're almost there. We have dy du, not dy dx. So I can just use the chain rule and multiply it by du dx. And again, the notation will help us out to see. Let me actually multiply on both sides first, du dx. But as you can see from the notation, the du's cancel out and you're just left with dy dx. So now we have f prime of u is times du dx. du dx. Now, what is du dx? So du dx is actually something we can evaluate. We said u was equal to g of x. So we just take the derivative. We'll get du dx is equal to g prime of x. Since we already know this is with respect to x, we could just put g prime. So let's get this back in terms of x instead of having u's everywhere here. So we still have our f prime of, and we said u was g of x, and then times du dx, or I'm sorry, g prime of x. I already had the du dx. So we'll say g prime of x. So it'll actually be helpful if I've written this in a red marker instead. So this is g prime of x. We can write this as du dx. Other than that, there you have it. This is another way to write the chain rule in terms of function composition. So let me actually place all this. As we said before, this is equal to dy dx. And the statement we claimed before that dy dx is f of g prime of x, we just put that in there. And there you go. So the derivative of a composite function is the derivative of the outside function, leaving the inside alone, times the derivative of the inside. Now that's actually very important to follow, so I'll say it again. The derivative of a composite function, let's say f of g of x, is the derivative of the outside, leaving the inside alone, times the derivative of the inside. So if that's still a little fuzzy for you, or can't see too clearly, we'll actually go through a few examples in the next video. So stay tuned.